Hello everybody, I hope you're doing well. Welcome back to another video reviewing your probability and statistics fundamentals. It's so great to be with you guys today on a Sunday evening. So today in this video, we're going to be talking about the sampling distribution, and we're actually going to be touching upon this topic in a couple of videos. So stay tuned for that. And the reason why I want to talk about sampling distributions is this idea is a very fundamental concept within statistics. So I thought it's kind of worth covering that. In the past videos, we've been talking about some probability theory, but we're going to shift gears and talk about statistical theory, right? And see where does the statistical side come in, basically. So we're going to start with talking about sampling distributions, right? So to motivate the topic, I think the way to understand sampling distributions is more of to understand it like an analogy, right? So imagine this scenario, right? We have a lake, right? And our goal is to measure the mean fish length. Now, one might ask, can I just go and catch all the fish in the lake and then measure up those fish lengths and then take the average and then we're done? Well, if only the world was so perfect, we could simply do that, right? But what if the lake was really huge and there's like thousands upon thousands of fish, right? It'll be really hard to capture all those fish, measure their fish lengths, and then like take the average and then call it a day, right? So that's difficult, right? But what can we do instead? And how can we come up with a more informed way to measure the mean fish length without having to do something very labor intensive, right? So what we're going to do is take advantage of the idea called a sampling distribution, right? So imagine this. What if instead of capturing every single fish possible in the lake and then finding the mean fish length, what if we capture a large enough sample of fish? So maybe say we capture 40 fish, right? We capture 40 fish. We're going to take the lengths of each of those 40 fish. We're going to take the average and then let the fish, back into the lake. And then the next day, we're going to do this experiment again. Collect 40 fish, find the mean fish length among those samples, right? And let's say we repeat this process like, thousands upon thousands of times, right? What we're going to get is, in each sample of 40 fish, right? We won't necessarily get the same mean fish length, right? But instead, you'll get a range of possible mean fish lengths. And in fact, we can actually visualize this in the form of a distribution. So what do I mean? So let's take a look at this above drawing. So suppose this axis is the mean fish length, right? And on day one, I'm going to go and take a sample of 40 fish, measure the lengths, and then take the mean of those lengths. And I'm going to plot that here, right? Okay, day two, I'm going to do this process again. I'm going to plot some mean value here. Day three, get another mean fish length. Day four, get another mean fish length. Day five, get another mean fish length. Day six, day seven, day eight, day nine, day 10, day 11, day 12, day 13, day 14, day 15, day 16, day 17, day 18, day 19. And you're kind of seeing the idea, right? Every time I take the sample of 40 fish, I'm going to get a mean fish length and plot that in a distribution, right? Now, I'm going to keep doing this process. And what do we notice here? When I look at this distribution, right? If I do this experiment of measuring, 40 fish and getting the mean fish length every single time, right? And I repeat this upon, a lot of times, right? I repeat this process of collecting the sample of 40 fish and measure the mean fish length. What you're going to get is actually a distribution of possible mean fish lengths. And just so it turns out in this drawing, right? We can actually fit this type of bell curve to it. Now, if you had paid attention in my previous videos, you'll recognize that this bell curve goes by a normal distribution, right? So it turns out that if we get a large enough sample, right, and we are able to, repeat the process of, getting this large sample and taking the mean and then plotting it in a distribution as such. So imagine the fish story, right? We would actually get a distribution of means whose shape is approximately normal, right? So essentially, if I go on to, some other day, measure 40 fish and get the mean fish length, I'm going to have some more plots here, right? So more means are getting plotted. So each of these red dots is going to be representing one sample's mean, right? Right? Because I'm repeating the experiment a lot of times, right? So that's what this is going to look like. And you'll see that this distribution, right, this shape is approaching more of that of a bell curve, right? So we've actually discovered something really nice here, right? I didn't have to know, like, inherently what was my distribution of mean fish lengths. All I could simply do is just collect a large enough sample get the mean, and then repeat that process a bunch of times to get some informed judgment of the shape of the distribution. And that, my friends, is a powerful theorem. We actually call this the central limit theorem, right? I'm going to abbreviate it as CLT. So central limit theorem, right? Now, what does the central limit theorem tell us? It tells us if we have a large enough sample size, right, then when we take a distribution of sample means, right, as such, we're going to get a shape that's approximately normal, right? Now, one question you might ask naturally is, how large is a large enough sample? Well, statisticians have determined that the rule of thumb is when the sample size is bigger than 30, right? So at least 30, we can actually say that the sampling distribution is approximately normal. So this is actually a very powerful theorem within statistics, right? So just by getting a sample size at least 30, right, the distribution of the sample means is actually going to be approximately normal, and we don't have to do a lot of work and engage in such a labor intensive process just to estimate one statistic, which is the mean in this case. Now, speaking of the word statistic, I'd like to draw your attention to two things, right? There is a distinction between statistic versus parameter, right? So what is a statistic? A statistic is any measure that describes a sample. A parameter is any measure that describes a population. So the way I remember this is sample, statistic, population, parameter. And you'll see what I'm doing here when I'm writing this out. I'm bolding the letter of statistic and sample. The first letter of both those words are S. In the case of population and parameter, the first letters are P, right? So sample statistic, population parameter. Sample statistic, population parameter. So hopefully that clarifies the distinction between a statistic versus a parameter. So let's study a little bit more about the sampling distribution of the mean, right? So it turns out for the sampling distribution of the sampling mean, right? So this, drawing I have here with the fish story, the mean is equal to the sample mean, right? So our approximation of the population mean is whatever sample mean we get, right? And that seems to make sense logically, right? So when we collect a sample, we might think the population mean is, that sample, right? Assuming that we are sampling kind of, in a relatively unbiased way and in a representative manner, right? We can reasonably say that our sample mean is that of the population mean. So that's what this first idea is telling you. The second idea is the standard deviation of the sampling distribution, right? So obviously the spread of the sample is affected by your sample size, right? So it just so turns out that the standard deviation of the sampling distribution, so baby sigma x, the symbol right here, is going to be your standard deviation over the square root of n, where n will represent your sample size. So let me jot this down. So sigma is going to be standard deviation. Mu is going to be the mean. X bar is the sample mean. And S sub x is going to be your sample standard deviation. And n will equal your sample size. So that's what these variables mean. And we're going to need to know this in order to solve problems, right? So what can we answer with the sampling distribution? Well, if I have the sampling distribution, I could say, for example, if I get a sample whose mean was, say this number here shown in blue, what is the likelihood of getting, a sample whose mean is less than that of this blue tick mark? We can answer questions like that just from knowing the sampling distribution. Now, in terms of making this more concrete, let's actually dive into a brief example. So in example 1, we're actually continuing the fish story. So we're trying to measure the mean fish length in a lake. And we catch a sample of 40 fish and find that the mean length is 4.15 with a standard deviation of 0.15. We want to find the probability of obtaining a sample of 40 fish where the mean length is at least 4.5. So what do we know here? So in problem 1, right? We know that the sample mean x bar equals 4.15, right? We also know that the sample standard deviation S sub x equals 0.15. We also know that our sample size is 40 fish. And what do we want to find? We want to find the probability of getting an X bar or sample mean that is above 4.5, right? So we want to find this value here, right? So let's take a look. We have the sample size is 40, right? But what did I mention earlier? Well, we see that 40 is greater than or equal to 30, right? So this sampling distribution is approximately normal, right? So now all we need to do is find this mu and standard deviation of the normal distribution. So, you know, in our approximated normal distribution, our mean would be x bar, which is 4.15, right? So we know mu is 4.15 in the case of this sampling distribution, right? Because we are using the normal approximation by the central limit theorem. We also know that um, S sub x, sample standard deviation, is 0.15. And from above, we observe that the standard deviation is simply the sample standard deviation divided by the square root of n, right? So our standard deviation for the normal distribution is 0.15 divided by the square root of 40, right? So we have the information we need. So we're using a normal distribution whose mean is mu equals 4.15 and sigma is going to equal 0.15 divided by the square root of 40. Now, given that we know this normal distribution, what is the probability of getting an x bar above 4.5? Well, since we have a normal distribution, we want to calculate a probability from a normal distribution. So we have this curve, right? And this will be 4.15. 4.5 might be here. We want this area here in blue. So if you recall from the previous video, to get probabilities from a normal distribution, we have to find the z-score, right? So the z-score will be 4.5 minus 4.15 over our standard deviation, which is 0.15 over the square root of 40. And that is going to equal, let me put this in my calculator real quick. So we have 4.5 minus 4.15 over 0.15 over the square root of 40. That will give us 14.75. So we have a z-score of 14.75. So we want to find the probability that z is at least 14.75. So we're going to look in our z-table, right? So we have this z-score, right? So this guy will be 0 and 14.75 is all the way here, right? We, in other words, want this blue area. But our z-table will give us the area here shown in green. So we're going to have to subtract out the green area. So I'm going to look for in my z-table and look for a z-score of 14.75. Okay, so unfortunately, I don't have a 14.75 in my z-table. So, but it looks like with the z-score of 3.49, the probability of getting a z-score less than 3.4 is 0.9998. So this is going to be approximately 1 minus 0.9998. So this is probably like, something a little bit smaller than 0.002. So we essentially have like a very low probability of getting, this extreme of a sample mean, basically. So that's kind of how the first example works. So it's really all about using your z-score and your tables to essentially get the probability you're looking for. So that takes care of example 1. Example 2 is a little more interesting. So we're going to instead shift focus from the fish problem to measuring the mean time cars are parked in a parking lot. So we're measuring the mean time that cars are parked in a parking lot. And unfortunately, the lot we're observing is not very busy, so we don't see a lot of cars. But what we're able to gather is that we have a sample of 15 cars, and we find that the mean duration, right? So the mean amount of time for which those 15 cars are parked is 20 minutes, right? With a standard deviation of 2 minutes, right? We want to find the probability of obtaining a sample of 15 cars where the mean duration for which the cars is parked is between 15 to 30 minutes. Okay, let's break down this example, right? So what do we know? We know we have a sample size of 15 cars, right? We know that X bar, right, is 20, right? That's the mean time at which those 15 cars are parked in the lot. We also know that our sample standard deviation is 2, because that's like the standard deviation we were given in the problem. We want to find this probability, right? We want to find the probability of getting samples whose mean is between 15 and 30. So we want to find essentially this value, right? So this is like essentially the question mark, right? All right, let's take a look. So we know the sample size is 15, right? But when we look at our central limit theorem, we see that 15 is not bigger than 30, right? So we cannot use a normal approximation, right? So cannot use a normal approximation for this problem, right? So the question is, if we can't use a normal approximation, how on earth are we going to find these probabilities? Well, it turns out we have another distribution we can use. We instead will use what's called the t-distribution. Now, how does the t-distribution differ from that of the normal distribution? So the z-distribution, right? Well, so this is the z-distribution in black. The t-distribution will look more of something like this. So as you can see in the t-distribution, right, in blue, right, the tails are a little bit more fattened out, and the t-distribution will have what's called the degrees of freedom, right? And degrees of freedom will equal the sample size minus 1. Now, I'll show you where to use that when we actually do the calculation, right? But that's just a distinguisher between what the t-distribution versus the z-distribution is, right? And the benefit of the t-distribution is that we can still get probabilities, but with relatively small sample size. So let's actually calculate this probability. So we see we have a compound inequality. So the probability of 15 less than or equal to x bar less than or equal to 30. It's just going to be p of x bar less than or equal to 30 minus p of x bar less than or equal to 15. So we need to get these two probabilities. So let's start with this first term here. So we need to get the t-statistic. We need to get like, the value or some kind of score to be able to look up in the t-distribution, right? So we have what's called a t-score, right? And the t-score is computed the exact same way as the z-score. It's simply x bar minus mu over over the standard deviation, right? But what do we know for this? We know that our mu in the case of the t-distribution is just the sample mean, right? So that's going to equal 20. We also know that the sigma in our t-distribution will be equal to the sample standard deviation over the square root of n. So this is going to be 2 over the square root of 15, right? So we have our sigma for the t-distribution, and we have the mean for the t-distribution up here. So we just need to calculate the t-score. We calculate it in the exact same procedure as the z-score, but we're going to use it as a t-score instead, right? So t as in Tom, right? So this is going to be the probability of getting a t-score less than or equal to 30 minus 20 over 2 over root 15 minus the probability of getting a t-score less than or equal to 15 minus 20 over 2 over root 15. So let's actually get these t-scores, like actually compute this out. So it'll be 10 over 2 over root 15. So this will be like the probability of getting a t-score less than or equal to 19.36. This term will be probability of getting a t-score less than or equal to be negative 9.68. All right, so we're gonna, and since we have a sample size of 15, the degrees of freedom will be 15 minus 1, which is 14. So we're going to use this to look up our t-table, right? So what do we see in our t-table, right? So we have our degrees of freedom on the rows, and these entries in here represent t-scores, right? So what I'm going to do is we have the t-score of 19.36 and a df of 14. So I'm going to go to the row where the degrees of freedom is 14, and I'm going to move right until I find the point where I hit, a t-score that's above 19.36. So in degrees of freedom of 14, I don't really hit a t-score of above 19.36. So we're going to say that the probability is 0.0005, right? So it's probably like, some probability much, much smaller than 0.0005. And then for getting a t-statistic of, less or equal to negative 9.68, we can take advantage of the fact that the t-distribution is symmetric. So basically, like, uh, actually, I lied a little bit. So we see here when we are going from degrees of freedom of 14 and we're just looking for the t-score above 19.36, these probabilities right here correspond to the chance of getting a t-score higher, basically. So for a degrees of freedom of 14 and a t-score of like roughly 19, the chance of getting something more extreme is much, much smaller than 0.0005. So basically, we're going to get a probability much, much bigger than 0.9995. Let me make this a little clear though. So you need to be careful about reading these like charts to know what they actually represent. And likewise, for getting a t-score that is much more extreme than 9.68. So if we have our t-distribution and we have negative 9.68 here, we want this green area, but we could alternatively take this green area instead because of the symmetric nature of the distribution, right? So we can convert this probability into probability of getting a t-score above 9.68, right? So now we look in our t-table, degrees of freedom is 14. We move to the right until we hit a t-score of above 9.6. And it looks like here the probability of such happening, of getting a t-score higher than like 9.68, is a number much smaller than 0.0005, right? So this is going to be a number much smaller than 0.0005. And we subtract these two, right? So we're essentially getting a probability much, much bigger than 0.9990. So you can say that the probability in this case would be 0.9990. Approximately, right? It's a very rough approximation, but this is kind of our probability. So all it's a matter of is just, using your knowledge of standardization, using the t-score, the z-score, checking for normality, using the central limit theorem, which is basically seeing if the sample size is at least 30, and just, applying the formulas, right? So getting the mean of, the Z or T distribution and getting the standard deviation using these properties up here. Now, there's one last thing I'd like to mention, though. So, in the central limit theorem, we've presented a heuristic where if the sample size is at least 30, we can just simply say that sampling distribution of the mean is approximately normal. But what if we get a small sample size and we know that the underlying distribution of the population is normal? If we know a priori, like in the problem statement, that the sampling distribution or the sample is drawn from a normal distribution, we can essentially bypass the CLT check and just simply use the Z distribution, even on a small sample size. But if we don't know the underlying distribution, so basically both these examples don't tell us where we're getting, the sample from, like are we sampling from a normal distribution? We don't really know that. So this is why in both these examples, we have to use the central limit theorem as a check to see if we can assume, the Z distribution or if we should use the T distribution instead. So that's pretty much a wrap for sampling distribution of means. Hopefully you kind of have a good understanding of, these example problems and how to apply the properties of sampling distribution of means to whatever problem that interests you. So looking forward to seeing you in the next video.